I'm going to give you my version first, and then I'll go through the version of Schwartz, which, I mean, they're related, of course, but I don't know. This Orthodox way of doing it strikes me as being almost closer to law than physics. But, all right, well, anyway, let's start with what we're talking about. Schwartz uses an abbreviated notation, which is just these brackets. By that, he means the time-ordered product of whatever's there in the vacuum. And we write that as, of course, in Fourier space, whoops, that's a 4. E to the minus I, P, x minus y, I, G of P slash, and what we know from last semester is that G0 of P slash, or IG0, is 1 over P slash minus M. I guess I could put it plus I epsilon, just for completeness, and that symbolically is written in the Feynman diagram is just a line. Now, the next order term in perturbation theory is G2, and the Feynman diagram looks like this, where there's a photon going across, and so the thing looks like this: P, K, P, and P minus K if this propagator is going this way. Although with the photon propagator, you don't need to say which way it's going, because it's the square of the momentum that enters. But I like to put an arrow there anyway, because then we see that P goes to K and P minus K and then recombine as K, and we have full momentum conservation at each vertex. All right, well, we can write this as IG0 of P slash, I sigma 2 of P slash, IG0 of P slash. And the sigma 2 then is basically this Feynman diagram here without those propagators. And so I'll write it here, I sigma 2 of P slash is, well, it was a minus IE at each of these vertexes, a gamma mu here. There's in the propagator in Feynman gauge, there's an eta mu nu here, so the gamma mu and gamma nu just become 2 gammas. And so what we get is minus IE squared integral d4 k 2 pi to the 4th gamma mu. By the way, I might say one thing here. These things are 4 component spinors. So there's an alpha here and a beta there. And this thing is a matrix. So this is the alpha beta matrix element. There's the matrix in the lowest order one, and you think of this whole thing, the inverse, as a matrix, and then you take the alpha beta component. All right. So I'm going to suppress that from now on. This is then I K slash plus M, a gamma lower mu k squared minus m squared plus I epsilon. So this is the electron propagator, the electron positron propagator, the fermion propagator. Then the photon one that comes along is minus I over p minus k squared plus I epsilon. Okay. And let me just mention that there is, we'll find out, there is an infrared singularity in this diagram. And I think actually that the way to handle the infrared singularities is to realize that I think it's probably that one should have been using coherent states all along rather than single photon. And this is a single photon states, and that it is particularly true in the infrared region where the energy of the photon is going to zero. Well, if the energy of the photon going to zero, you expect to have more than one. And so, but that's something that Schwartz treats out of chapter 23 or something. And let's hope we all live so long. Okay, so that's our diagram here. And we're going to manipulate that in a minute. In fact, since it's sitting there, I almost think I should manipulate it right away. So let's look at this gamma mu term. I think this is the thing that actually puzzled me on Tuesday when there was a certain diagram where we had gamma mu, k slash gamma mu, and all of a sudden thing changed completely. The reason is that you can write this in this way. If this is k slash and then you have a gamma mu, well, of course, that's gamma mu, gamma nu, k nu, gamma mu. Okay. But the gamma matrices are defined so that their symmetric product is 2 eta mu nu. And so we can rewrite that as minus gamma nu gamma mu plus 2 eta mu nu. And then you have k nu gamma mu. Okay. And now it all of a sudden makes a lot of sense. The k nu with the gamma nu gives us a minus k slash. We then have gamma mu, gamma mu. Well, if one gamma is up and the other, one mu is up and the other mu is down, you just get the identity 4 times. So this is 4. Then this one is plus 2 eta mu nu, k nu, gamma mu. Well, that's just k slash again. So altogether, this is minus 2 k slash. The other term there is m, gamma mu, and this is just 4m. All right, so that's what we're going to do to this to simplify it. And Schwartz writes some of this as IG of P slash, which is the full propagator, as something that looks like this. And the idea is that this is the lowest order one plus the thing that we're going to be calculating now plus higher order terms. And so this is I over P slash minus, and we're going to be leaving out the I epsilons, I guess, just from I epsilon fatigue. So let me put one in, plus I epsilon there. P slash minus m, then I sigma 2 of P slash I over P slash minus m, and then I rho. Okay, so that's what we're looking at here. Now, if we keep track of these i's, there's a minus sign here. I times minus I is 1. Somehow I have the feeling that I've missed a minus sign. This is I sigma 2. Yeah, I think, I'm still puzzled. Minus sign, oh, of course, there's an overall minus sign. This is a minus sign, I minus I is 1, so the overall thing is a minus. All right, anyway. So what we get then is that this is equal to e squared integral, and let me pull out the 0 to 1 dx. This is after we use the Feynman trick and combine the denominators, these two denominators. And so what we get is 0 to 1 dx integral over all k, d4th k over 2 pi to the 4th, and then what's left is 2k slash minus 4m, and then the Feynman trick here gives us k squared minus m squared, 1 minus x, plus p minus k squared x, plus I epsilon, and this thing is squared. Okay. So what we've got is a logarithmic divergence, and I think what that divergence is telling us is that the theory doesn't know about what's going on at short distances, and so we can't really compute anything. Let's make the shift. K goes to k plus px. And actually, when I'm saying logarithmic divergence, there is a linear divergence in this k. But the k, it turns out, especially after you make the shift, it looks like this. I sigma 2 of p slash is 2e squared 0 to 1 dx d4th k 2 pi to the 4th, and then x p slash, so this is after the shift, minus 2m over k squared minus delta plus I epsilon squared. Okay, well, delta is 1 minus x times m squared minus p squared x, so it doesn't involve k at all. So this is even in each component of k, so if there's something linear in k in the numerator, it would cancel. Just because, you know, like the integral of x over x squared dx over a symmetric limit minus r to r would vanish. So, okay, and remember in the shift, you see, when we say here, this is k and that's p minus k, this is quite arbitrary. We could have said this is k plus px and this is p minus k minus px. We could have done that here. So the shift is, it's legitimate, although, as I said, because these computations all seem to involve divergent integrals, everything is a little bit suspicious. All right, anyway, what I'm going to do is rewrite this as 2e squared integral 0 to 1 dx, and I'm pulling out x p slash minus 2m because they aren't involved. So here's where I'm departing from Schwartz. I'm doing this thing in a simple way, and it turns out that we'll get basically instantaneously the result he gets about 8 pages later. On the other hand, can one systematize what I'm doing? I don't know. Okay. So what I'm going to say then is that this is an integral from delta 0 to delta d delta of the derivative, or maybe I should just say d delta of what's left, which is this integral d fourth k over 2 pi to the fourth 1 over k squared minus delta plus I epsilon squared. And then plus, what would that be? Well, if I call this thing 2e squared integral 0 to 1 dx x p slash minus 2m sigma 2 hat of p slash, then is that, do I want to say this? I want to say this is sigma 2 hat of p slash. But anyway, it's whatever this thing is. Yeah, I think that's fine. All right. Anyway, it's some term that, since this thing is a number, it's some number, and a more complete theory would compute it. Instead, we'll just say we're going to compute the change, and then we fit the change to experiment or whatever. Well, the derivative of this, of course, is minus 2, or actually plus 2 because of the minus sign. This thing to minus 3. And so what we've got here is that I sigma 2 of p slash then is 2e squared integral 0 to 1 dx xp slash minus 2m integral delta 0 to delta d delta of integral d fourth k 2 pi to the fourth 2 over k squared minus delta plus I epsilon, and now this is cubed plus, I'll just call this sigma hat of delta 0. That's what I called it in my notes. Okay, well, we now do the Wick rotation, and after the Wick rotation, this turns out to be a particular integral that you can find. I don't know, it's b dot 239 or something. Which almost sounds radioactive. Anyway, so this is 2e squared integral 0 to 1 dx xp slash minus 2m. And now we've got an integral from delta 0 to delta d delta, and this is minus I times 2 over 2 4 pi squared 1 over delta plus the sigma, I'll just call it sigma hat 0. This 2 is that 2. The integral is minus I over this. So I'm using the integrals that we use in dimensional regularization, but I'm just setting, in this case, d equal to 4 directly because the integral is finite. Okay. And now this is pretty simple, namely, well, why don't I go up here? So in other words, we're going that way. This is then 2e squared minus I over, it turns out to be 32 pi squared. Favorite number in quantum field theory. 0 to 1 dx x p slash minus m integral delta 0 to delta d delta 1 over delta plus, I'll just pull out sigma hat. And this is then log, so this thing is minus 4ie squared over 32 pi squared 0 to 1 dx xp slash minus 2m log delta over delta 0, I guess I should say plus sigma hat 0. Okay, well, canceling some simple integers, this is minus I e squared over 8 pi squared 0 to 1 dx xp slash minus 2m log 1 minus x m squared minus p squared x, and I'm going to absorb these two things together and just call it u squared. So that's the expression I get. And then if we multiply by minus I, because we remember that what we're actually computing here is I sigma 2. So we multiply both sides by minus I. That gives a minus sign here. The minus sign on the log just flips the argument. And so we get sigma 2 of p slash is e squared over 8 pi squared is e squared over 2 times 4 pi. E squared over 4 pi is alpha. So this is actually alpha over 2 pi. Oh, sorry, this was a pi squared. Well, there. Alpha over 2 pi, integral 0 to 1 dx, x p slash minus 2m log u squared over 1 minus x m squared minus p squared x. All right, so that's what we get. And now if you compare that with one of the later formulas in Schwartz, you see this is what he gets also, although he has an R on this, or an R on that, maybe twiddle her in there. But, so, I don't know, it seems to me that something like this makes a lot more sense, because in order to get his expression, he had to set something like delta 2 was taken to be infinite, and 1 over 1 plus delta 2 was approximated as 1 minus delta 2. And so, I don't know, I'm not, but now I'll just go through the, Orthodox treatment here. Gospel according to Schwartz here. And what Schwartz does is, first he does the Pauli-Villars regularization. And so he says, let me just blank this underneath. So he says, well, sigma 2 of p slash is minus 2i e squared 0 to 1 dx x p slash minus 2m d4 k over 2 pi to the 4th is 1 over k squared minus delta squared minus 1 over k squared minus delta prime squared, where delta prime is some, all right, let me say what is delta prime is. Delta prime is, in fact, I think it's simpler to write it in terms of delta. So delta is 1 plus x lambda squared, where lambda is something that you have to send to infinity. And so then you get minus alpha over 2 pi, 0 to 1 dx, 2m minus x p slash log x lambda squared over 1 minus x m squared minus p squared x. And Schwartz writes this as minus alpha over pi m log lambda squared minus a quarter p slash log lambda squared plus finite. Of course, the finite is the part you're interested in, but anyway. All right, so this is Schwartz's approach with Pauli-Villars. He also does it for dimensional regularization. And then what he has is symmetry p slash is minus 2 pi e squared mu, which is just an arbitrary mass that's finite, 4 minus d integral 0 to 1 dx x p slash minus 2m integral dd k over 2 pi to the d. So d is something like 4, or 3 minus epsilon. Yeah, 3 minus epsilon coming down. 1 over k squared minus delta plus I epsilon squared. So the next thing is do the Wick rotation and then integrate pretending that d is not 4. And then what you get is minus alpha over 2 pi, 0 to 1 dx, 2m minus x p slash 2 over epsilon plus log u tilde squared over 1 minus x squared minus p squared x. And u tilde squared, well, you want to keep the electron's charge dimensionless. In d dimensions, electric charge has dimension. And so you absorb that into the u tilde. U tilde squared is 4 pi e to the minus the Euler-Mascheroni constant, which is about 0.6, being very crude. U squared. And Schwartz rewrites this as alpha over pi times p slash minus 4m over 2 epsilon plus finite. And, okay. All right, so the next business is renormalization, and Schwartz recalls that our action looks like this. Okay. And the traditional view of renormalization is, well, we've got these constants here. We don't know what they are. They just occurred in the action, and maybe they're a finite mass. Maybe they're a half an MeV plus infinity, and this one is whatever we did in chapter 17 to cancel the infinities there. I don't really mind that approach. What bothers me is that then these things are treated as small numbers and as infinite numbers. And I don't know, I find it appalling.
So is that a Schwarzism?
No, 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 it's got nothing to do,
So that's
I'm not
just a-
blaming Schwartz, this is the traditional view.
So the traditional view is sometimes they're small, sometimes they're
Oh.
infinite.
Yeah, and, you know, I don't know. I've never seen a decent treatment of this that persuaded me that it wasn't nonsense. But that doesn't mean that something doesn't exist, and that's better. What Weinberg does is he treats it as briefly as possible. and yeah. All right, anyway, let's just go on with the song and dance, because it's something that you should see. And let's hope that somebody clears this up at some point. So we're going to let this E0 be some finite number plus ER squared times pi 2 of P0 squared. And this thing is, Schwartz calls it formally infinite. I don't know what that means, formally infinite. It's either infinite or isn't. All right, anyway. Okay, ER, but as I said, this is the traditional view, and so I'm not blaming Schwartz. ER squared, 12 pi squared, log lambda squared over minus P0 squared plus blah, blah, blah. So this is basically what we did in chapter 17 when we weren't just doing the subtraction method, the differentiation method. Okay, and so we've got IG2 of P slash I over P slash minus M0 plus I over P slash minus M0 I sigma 2 of P slash I over P slash minus M0. So the idea is to use this, the infinity in M0 to cancel the infinity of 2 over epsilon. And the problem, though, is, you see, you've got a mass here, and so you could write this as M renormalized plus delta M, and cancel the delta M over the epsilon, but then you've got this guy, and that's different. And so you need a different kind of renormal. You need a third infinity. You need 3 infinities to work things out. So basically, this infinity is the one that got fixed in chapter 17 and gave us the renormalization of the photon propagator. And now we need something else. Well, the something else is that the normalization of the field, our field, of course, is this standard sum over spin integral d cubed p 2 pi cubed square root of 2 omega p, and then a of p and s, u of p and s, using the correct spinners, of course. E to the minus I px plus b of p and s dagger v of p and s and e to the I px. Now instead, what we're going to say is that psi renormalized at x is going to be 1 over square root of z2 psi 0 of x. Well, I don't think we need to write it down. And this is another one of these numbers that's formally. Okay. So the idea is that at tree level Z2 is 1, and so we're going to set Z2, well, the standard thing is to say Z2 is 1 plus delta, to say that M0 is some Zm times m renormalized, and that Zm is 1 plus delta m, so piece of m is 1 plus delta m, and so this m0 is m renormalized plus m renormalized delta m. And so psi 0 of x, psi 0 bar of y is I before p over 2 pi to the fourth. This is the ordinary Feynman propagator. I'll just write this as G. I don't know why you didn't just use G0. I think I'm just going to use G0. Well, no, G bar of P slash. And psi renormalized x, psi renormalized bar of y, well, this thing would be ditto, but G renormalized of P slash. And the idea is that this is finite and that one isn't. And in fact, since renormalized and unrenormalized is differed by this Z2, root Z2, what we've got here is that G renormalized of P squared is 1 over Z2 G bar of P slash. Okay, so anyway, this is the standard way that this is done. And so what do we have? I think I'll use this board later because right now I need something here. So I G renormalized at P slash is then 1 over Z2 I over P slash minus M0 plus loops. And so what is this? This is 1 over 1 plus delta 2. That's what Z2 is. And this one is I over P slash, and now M0 is MR plus MR delta M. Plus loops. Okay, now get a load of this. This is what one actually does. So let me put in the intermediate steps, which I think are rather embarrassing. This is then written as 1 minus delta 2. And this thing is going to be written as I over P slash minus MR. And let me just try to figure out quite how, I don't even quite see how this is done, because in order to do this 1 over, I mean, it seems to me that one is, oh, that's right, we've got an MR here. All right, so in other words, we say that this thing I'm trying to do the arithmetic. See, normally, I mean, you can certainly do 1 over, but what they're going to do is to throw this upstairs. Oh, I see what it is. Okay. All right, so when you toss this part upstairs, what you get is minus delta M MR over P slash minus MR. So 1 minus. Okay, so in other words, this thing here we write as this. Maybe I should do this in 2 steps. Yeah, I think it's right too, but maybe we'll do it in 2 steps. 1 minus delta M MR over P slash minus MR. Okay, plus loops. And so now this is 1 minus delta 2 I over P slash minus MR. And then up here, what we've got is 1 plus, no, 1, that, and 1 over that is just this. It's 1 plus. Okay. So altogether then, we've got in the numerator these delta 2 and delta M, and this is then I over P slash minus MR plus, we've got 2 of these guys, so we have I over P slash minus MR. Then we have I delta 2 of P slash minus delta 2 plus delta M times MR I over P slash minus MR plus loops. Okay, but this is assuming that delta 2, which is infinite formally, and delta n, which is formally infinite, are small numbers, and you can do this expansion. So, I mean, this sort of stuff just, I mean, how can you take it seriously? I just don't know. But it's the official dogma. And when one objects, the response is, but it works. Well, of course, the thing I wrote down works also, and at least I didn't have to assume that anything, something was formally infinite and also very small. Anyway, what you have then is I renormalized at P slash is I over P slash minus MR plus I over P slash minus MR I delta 2 P slash minus delta 2 plus delta M and R plus sigma 2 of P slash I over P slash minus MR plus higher order terms. So the loops came in that way. Okay, now we've got these terms that are small but also infinite, and we can use them to cancel the terms in here that are infinite. And so that's the next step. What does one do? Well, if you're doing the Pauli-Villars, in fact, why don't I just come over here and then use up this blackboard. If we're doing Pauli-Villars, we say delta 2 is equal to minus alpha over 4 pi log lambda squared, and delta M is minus 3 alpha over 4 pi log lambda squared. And if we're doing dimensional regularization, then we say delta 2 is minus alpha over 4 pi 2 over epsilon and delta m is minus 3 alpha over 4 pi 2 over epsilon. And epsilon is, I guess, 4 minus delta. And so, curiously, the divergences are different. This is linear as d goes to 4. This is log as lambda goes to infinity. All right, well, these different things are called different subtraction schemes for obvious reasons, that we're canceling infinities by subtracting them. There are basically two that are used in modern calculations. One is called minimal subtraction, the other one is called modified minimal subtraction. So that's MS, and modified minimal subtraction looks like that. And basically this thing, the mu loses the tilde. Okay, there's also an on-shell method, but on-shell subtraction, but apparently these two are used more commonly now. Okay, I've been going on quite some time here. There must be a couple of questions before we continue.
Nothing beyond just asking why this even works. Why you can do this delta is infinite.
Well, I've asked myself that question and never come up with an answer. That's why I think instead it's better to, I mean, this method of differentiating and saying that we really can't compute anything, but we can only compute how this thing changes as we change this scale, in this case delta. This seems both simpler and more honest. But as I said, I'm not an expert in this, so maybe this stuff was started back in the 40s and by Schwinger, Tominaga, and Feynman, and then subsequent people made it more and more elaborate and formalized. And as I say, the treatment here in Schwartz almost sounds as though it's in a law book as opposed to a physics book. Anyway, let's just notice that G bar of P slash, what do we have? We have that plus, well, these are some of the diagrams. And these ones you can basically sum up. It turns out that they form a geometric series. I over P slash minus M0, I over P slash minus M0, I sigma 2 P slash I over P slash minus M0, plus, and then again I over, well, I'm just going to write it this way. And so forth. And so what you can do is you can sum that up. The trouble is, if you sum this up, you're leaving out other diagrams. And so what people did, and is they realized that you could form another geometric series, and that what you had to do was at any point you had to include all what are called one particle irreducible diagrams. And so, for example, this is one particle reducible because you can cut one line and you have two disconnected diagrams. This one is not one particle irreducible. And so this one is said to be one particle irreducible. All right. And then what you can say is that if you consider all of the one-particle irreducible diagrams, and that would be an infinite set of diagrams, of course, you could then say that Ig of P slash, whether bare or not, it would be the lowest order plus one particle irreducible plus, and now these guys you would be able to actually form a complete geometric series here, where these are all 1pi. So each of these is a sum, an infinite sum. And so then what you would get when you form that geometric series, you'd get that Ig of P slash then would be I over P slash minus M plus some sigma of P slash. And so this is a big deal. This is a sum of all the one particle irreducible diagrams. And so this thing would, for example, one of them would have to go in here, would be this one, which is a sixth order, e to the sixth diagram. That would go in there. So you see this is almost a bewildering complexity. Not to fear, we'll cancel these only infinite. Okay. All right, so I'm once again out of Blackboard space, so I'll go to this space that former chairman destroyed. That's why it's such a lousy Blackboard. Anyway, well, maybe I'll go up here. G bare then of P slash is this I over P slash minus M0 plus sigma 2 of P slash. And so the renormalized one is Ig renormalized of P slash is 1 over 1 plus delta 2 Ig bare of P slash. And one can rewrite that as 1 over 1 plus delta 2 I over P slash minus M0 plus sigma 2 of P slash plus higher order terms, and that's then I over P slash minus M renormalized plus delta 2 of delta 2 times P slash minus delta 2 plus delta M MR. Sorry about this quality of this Blackboard. Plus sigma 2 of P slash. And then one can rewrite this. So let me say IGR of P slash as I over P slash minus M renormalized plus sigma renormalized of P slash. Okay. So this is the standard thing. And now what's sigma renormalized? Well, let me see if I can erase some of the Blackboard here. Okay, maybe we should wait for it to dry for a minute. Does somebody have a question? It'd be a good time to ask questions. All right, let me just, while we're waiting for this to dry, it's almost dry actually. We could ask ourselves, how would we reformulate physics so that this differentiation mechanism would occur naturally in the formalism rather than as a sort of, the way I did it, where we had to say, well, we can't really compute anything except for how things change when we change the energy scale. Maybe we have to start with a formalism that has a lower goal than quantum field theory. In other words, the path integrals, we write down a path integral saying that the amplitude to go from this to that is this. Maybe we need to say something else that well, I don't know, but if we change scale, the change in the amplitude would be such and such. I don't know. Anyway, all right. Now that we've got a better blackboard, let me just recall where we were. So, we were there. Okay, what's this sigma renormalized? Well, keeping track of all of these terms, sigma renormalized then of P slash is sigma 2 of P slash plus delta 2 of P slash minus delta M plus delta 2 M sub r plus higher order terms. And the idea then is that these two different infinite constants cancel what we needed there. And why 2? Well, 2 because we need something to cancel the term, the infinity that was P slash over epsilon, and something else to cancel the infinity that was M over epsilon. That's basically why we want 2 of them. And what some people do is some people write the action density as I psi bar bare psi 0 minus M0 psi bar bare psi 0, and then rewrite it as I Z2 psi bar renormalized D slash psi, D slash psi renormalized minus Z2 Zm N renormalized psi bar renormalized psi renormalized. So with our definitions, we can rewrite them that way, and another way of writing them is I psi bar renormalized D slash psi renormalized minus M renormalized psi bar R psi R plus I delta 2 psi bar R D slash psi R psi renormalized minus MR times delta 2 plus delta M psi bar R psi R. Okay, so in other words, we do the calculations with these two things where everything's finite, and then we have these two sets of infinite terms, this one giving you a P slash thing, and this one just basically giving you a constant thing. Well, with on-shell subtraction, what we do is we want when P slash is the physical mass, we want this thing to change the renormalized, minus the renormalized mass into minus the physical mass. So one condition, which is called on-shell subtraction, is sigma renormalized at the physical mass of the electron should be MR minus and physical. So that's one way of fixing these terms. And another is that the pole should be in the right place and have the, I'm sorry, that's the pole being in the right place. The other is that the residue should be correct. And the residue that we want is just odd. So there better not be any extra residue coming here. So we say I is the limit P slash going to MP. And now you might say to yourself, what is going on here with P slash going to MP? What we really mean here is that P goes on mass shell. I think that's what's actually mean. In other words, P squared equals M squared. Anyway, he writes it this way. And what is this? It's that P slash minus MP times I over P slash minus MR plus sigma R of P slash, which is also limit P slash goes to MP, I over, and so we divide top and bottom by that, and we want to get 1 plus DDP slash of sigma R of P slash. And so this thing should vanish. In other words, the other condition is dP slash of sigma R of P slash on shell, which is P slash equal to MR equals 0. And again, P slash equal to MR makes no sense because P slash is a matrix. Or did we disconnect?
Where? Oh, okay.
So what happened? We had a gap? Or?
No problem, man.
No problem. All right. Okay, so that's the other condition. All right, these conditions then, what do they amount to? They amount to setting delta 2 equal to minus dDP slash of sigma 2 of P slash. Again, P slash equal to the actual physical mass. Well, now I'm a little bit puzzled. Are we doing pole mass as physical mass? Yes. Yes, physical mass, pole mass is the same here. And so delta 2 is that, and we also want delta M and P to equal sigma 2 of MP. And in Pauli-Villars, it rang and then it's gone. Pauli-Villars, what we have is sigma 2 of MP is minus alpha over 2 pi MP 3 halves log lambda squared over MP squared plus 3/4 and dDP slash of sigma P slash, again at P slash equals M physical, equal alpha over 2 pi, a half log lambda squared over MP squared plus 5/4 minus an integral 0 to 1 dx, 2x, 2 minus x, over 1 minus x. Okay, so what we see happening here is that as x goes to 1, becomes 2, this becomes 1, but this becomes 1 minus 1. So this is the infrared divergence. And as I say, there are ways of dealing with that don't involve the hocus pocus of things that are formally infinite, but in fact 0 or very small. But that's a later discussion. All right. So let me see here. I'm just wondering how much. In any event, after doing let me just go to, which is essentially the equation 18.62. Schwartz finally gets this expression. Sigma p slash is alpha over 2 pi integral 0 to 1 dx x p slash minus 2mr log mu squared over 1 minus x mr squared minus p squared x. Okay, but now if we compare that with the one that I got, somewhat simply we see that they're the same, except I don't have any subscripts. And there wasn't any need to introduce anything infinite. So let's see. I'm just wondering how. Let me just say what delta 2 and sigma are in dimensional regularization. In dimensional regularization, what we've got is that sigma 2 of p slash is alpha of 2 pi, this same integral 0 to 1 dx, x p slash minus 2m, 2 over epsilon plus log mu tilde squared over 1 minus x mp squared minus p squared x, and then plus a mystery term, x times the mass of the photon squared. That's to cure the infrared divergence, but as I say, that's not the right way to cure it. But anyway, delta 2 is minus sigma 2 prime at MP, and this is minus alpha over 2 pi, 1 over epsilon plus a half log mu tilde squared over p squared plus 5 halves plus log m gamma squared over mp squared, and delta m, well, let's see, that was delta 2. Delta m is 1 over mp, sigma 2 of mp, alpha over 2 pi, minus 3 over epsilon, minus 3 halves, log mu tilde squared over mp squared minus 5 halves. All right, there's the matter of amputation. What is amputation? Well, the idea is that these 1PI diagrams, or equivalently these loop diagrams, we have to include them when they're inside the diagrams, but we don't really need to include them when we're talking about the lines that are coming in. So in other words, if we're talking about some complicated diagram in which we have 2 to 2 scattering, we need to include all the loops that occur in here, but we don't need to add these guys. And the reason is that, at least the reason is that these things just change the, in other words, using the physical mass of the external particles is already a correction for all of the terms like this, and so we don't need to do that. We just use the physical mass for the ones that come in. So here Schwartz is referring to the LSZ formalism, which gave you a matrix element. An S matrix element is a bunch of differential operators on a time-ordered product integrated, and the differential operators essentially give you a P slash minus M on each of the, and the M there is the physical mass, or a box squared minus M, or, so that would be P squared minus M. Anyway, the section 18.4 gives a discussion of what the rules are for minimal subtraction and modified minimal subtraction, and then there's a summary and discussion. I encourage you to read that, but as I say, it strikes me as kind of legalistic, and so I'm gonna skip it, and we'll try to do 19 next time, and at some point we'll get beyond all this and deal with the standard model, which will make a lot more sense. All right, so any questions? All right, let's stop.